So the third question that we shall tackle in this video came in paper 2, May 2004, time zone 2, question 7i. This is a continuation of a previous video labeled review 3 part A. So this is review 3 part B. This continues on the previous video. So take a minute, pause the video, attempt to solve, and the answer shall follow through shortly. So in question A, you are required to sketch the graph of g of x, which is e to the power of x over x, and you are given the domain and the range which you shall use in your window settings, and the GDC sketch should look something like this, right there, and you should copy this sketch onto your paper. Now in question BI, you are required to find g dash of x. So I've written g of x in a different way. So the original function was e to the power of x over x. I've rewritten it as e to the power of x times x to the power of -1, and this shall help me use the product rule in order to evaluate the derivative. Of course, you could have just used the quotient rule to evaluate the derivative of this fraction, but I personally see that the product rule is easier to use. Hence, we shall use uv dash plus vu dash, and there is our v dash, there is our u, so this is uv dash, and there is our vu dash, so this is our v, and this is our u dash. So uv dash plus vu dash, and what I've done here is I've taken e to the power of x as a common factor and rewritten those as fractions with x in the denominator and positive powers. So instead of x to the power of -2, it became 1 over x to the power of 2. Instead of x to the power of -1, it became 1 over x. So this is my g dash of x. This is my derivative function. The reason why I did that is because this format shall help me solve the next question with more ease. So let's take a look. So BII requires that we calculate the exact values of the coordinates of the minimum point on the graph of G. We know that the minimum point is a point where g dash of x equals 0. Hence, we want to set this expression right there to 0. This format is much easier than this format when you're trying to solve this algebraically, because we know that e to the power of x shall never be 0. So this entire expression shall be 0 only when the second component, which is this bracket, is equal to 0. So I just need to solve this bracket, the second component, as equaling 0. So this is what I've written right there. I don't need to worry about the e to the power of x because this shall never be 0. So -1 over x squared plus 1 over x equals 0, and you solve this. I've taken 1 over x squared as a common factor, so I get -1 plus x in the bracket. Again, 1 over x squared shall never be 0. So I can repeat the same principle. Just like I've ignored this factor, I can ignore this factor because it shall never equal 0. So what remains for me to do is find the value of x that makes this bracket equal to 0, and obviously the value of x is 1. So this is useful particularly if it's a paper 1 question and you can't use the GDC to solve. Anyway, so in order to find the y coordinate, I shall substitute 1 instead of x in the original function. So I get e to the power of 1 over 1, or times 1 to the power of -1. That's the same thing. So whichever format of the original function you prefer, it doesn't matter. So g of 1 equals e, hence the point is 1, e. This is the minimum point. You are given in question C that the second derivative of g is g double dash of x given by this formula, and we want to explain why the graph of g can have no inflection point. So the given formula for g double dash is right there, and it consists of three components. We will repeat the same principle that I've just mentioned in evaluating each component separately. Now, 1 over x power 3, can this ever be 0? No, it can never be 0. So I can just cross it out. It doesn't matter. Now, e to the power of x, can this ever be 0? It can never ever be 0. So I cross it out. Now I need to solve this bracket as equaling 0 and see whether I have solutions or not. There are multiple ways to do that. You can either sketch it on the GDC and try to find the x-intercepts. You can attempt to use the quadratic formula. I've done that. I've just used b squared minus 4ac to see whether there are roots to this equation or not. Because as we know, the quadratic formula is negative b plus minus root b squared minus 4ac over 2a. So root b squared minus 4ac is the critical component. If b squared minus 4ac is negative, then there are no solutions because you cannot have a negative value under the root. So I've assessed b squared minus 4ac and I found it to be negative 4. So if I use the quadratic formula, I'm going to get root of negative 4, and this can never have a solution. Hence, even this component is crossed out. Hence, g double dash can never equal 0. And since g double dash can never equal 0, then there are no inflection points. So this concludes our third question. Take a minute to copy this down if you will. I shall begin question 4 shortly. So the fourth question that we shall tackle came in paper 2, May 2011, time zone 1, question 9. Kindly take a minute and attempt to solve, and the answer shall follow through shortly. So you are given the graph of f of x equals e to the power of negative x squared. And you are asked in question A to identify the 2 points of inflection. So where are the points of inflection on this graph? They are the points where the curve changes concavity. And by concavity, in simpler terms, we mean whether the curve is smiling or frowning. So up till B, you can see that this is a part of a smile. And from B to D, you can see that this looks more like a frown. And after D, from D onwards, again, the curve looks like a smile. So when the curve looks like a smile, this is what we call a positive concavity or an upwards concavity. So in these regions, f double dash is positive. Before B and after D, f double dash is positive. From B to D, this frown we call downwards concavity. And from B to D, we say that f double dash is negative. So the 2 points where f double dash changes sign from positive to negative, these are the 2 points of inflection. In other words, the 2 points where the curve changes concavity are the 2 points of inflection, which are B and D. In BI, we are required to find f dash of x. So we need to differentiate this function. So let's take a look at how to do that. So if f of x is e to the power of negative x squared, then f dash of x shall be e to the power of negative x squared as well, multiplied by the derivative of the inner function, which is the exponent. The derivative of negative x squared is negative 2x. Hence, this is the expression for the derivative function. Next, you are required to show that f double dash of x is this expression 4x squared minus 2 times e to the power of negative x squared. So we shall use the product rule to differentiate f dash of x, hence obtaining f double dash of x. So there is my u and there is my v. I'm going to find uv dash plus vu dash. So there is my u dash, this right there is my u dash, and this is my v. So this is vu dash. Next, I'm going to find uv dash. So that there is my u and there is my v dash. So this is my expression. Hence, f double dash of x equals e to the power of negative x squared multiplied by 4x squared minus 2. And the way I've obtained this is by first multiplying negative 2x by negative 2x, which gives me positive 4x squared, and then by taking out e to the power of negative x squared as a common factor. So when I take this out as a common factor, what remains inside the bracket is 4x squared and the negative 2. Hence, this is my final expression, which matches that which was given in the question. So moving on, I am asked in C to find the x coordinate of each point of inflection. And we know that points of inflection are points where f double dash equals 0 and changes sign from positive to negative or otherwise. So for the purpose of C, I need to set f double dash to 0 and find the values of x that satisfy the equation. So when we set this expression to 0, we are in fact only setting the second part of the equation to 0, the second part of the expression to 0, because we know that this component shall never equal 0. So you can just disregard it. So I just need to solve 4x squared minus 2 equal 0. And this is easily solved manually or by the GDC, whichever you prefer. I took the 2 to the other side, I divided by 4, getting x squared equals half. Hence, x equals either positive 1 over root 2 or negative 1 over root 2. Both values satisfy the equation. From the graph, I know that the negative value corresponds to point B and the positive value corresponds to point D. Next, in question D, I am asked to use the second derivative to show that one of these points is a point of inflection. So I need to choose either one of the 2 points and prove that it's a point of inflection. So in order to prove that it's a point of inflection, I need to test 2 properties. That f double dash is 0 and that f double dash changes sign. So in order to test that f double dash changes sign, I'm going to do this automatically, immediately, right there. However, the fact that f double dash is 0 is the property that we use to derive the point. So we already know that these are the 2 values that make f double dash equal to 0. So I've already proven this property. I now need to prove the property that f double dash changes sign for either one of these 2 values of x. I've chosen the positive value, you can choose whichever you like, and I shall test concavity before this value. So this value is 0 point something. So I shall test concavity at x equals 0 and x equals 1. I shall test f double dash before the point, so at x equals 0, and after the point, at x equals 1. So f double dash of 0 is obtained by plugging 0 into this expression, and I've obtained it as negative 2. F double dash of 1 is obtained again by setting 1 into this expression, and I've obtained it as 2 over e. So since it was negative when x is 0 and positive when x was 1, then I know that f double dash changed sign, and hence at x equals 1 over root 2, I do have a point of inflection. So by proving that f double dash changed sign, I have proven that this indeed is a point of inflection. So this concludes our 4th question and our video. Take a minute to write this down if you will. I hope you have found this video useful.